Section: Introduction. We, in the field of reinforcement learning, RL, often measure our progress by comparing new methods against established benchmarks. This comparison relies on having access to the data from these benchmarks or being able to recreate the experiments to generate new data. Being able to reproduce experiments is crucial not just for comparison but also for identifying where a method shines or falls short, guiding future research directions. However, we face several hurdles in this process. Often, the data we need for reference isn't readily available, forcing us to recreate experiments. This task can be daunting due to poorly documented source code and constantly changing software dependencies. Past studies have shown that even small differences in implementation can significantly affect outcomes. Moreover, the limited availability of computing resources can restrict our ability to reproduce these experiments, especially for researchers with limited access to such resources. These challenges make it difficult to evaluate new methods reliably and compare them effectively against existing ones. Reproducing experiments is not only time-consuming and resource-intensive but relying on inconsistently presented results from papers adds to the complexity. The absence of standardized metrics and benchmarks across studies further complicates comparisons, leading to a significant waste of time and resources. To overcome these obstacles, it's essential for the RL community to establish strict standards for reproducibility, ensuring that experiments can be replicated and compared across studies. Sharing data, code, and experimental details transparently, along with adopting consistent metrics and benchmarks, would greatly improve the evaluation process and accelerate progress in RL research. The Open RL Benchmark Initiative steps in to address these issues by offering a comprehensive collection of RL experiment data. This initiative focuses on using existing data to avoid the need to rerun baseline experiments, emphasizing reproducibility and transparency. Our contributions include providing a vast dataset of RL experiments, promoting the use of existing data to set new standards, including a wide range of metrics for detailed evaluations, ensuring easy replication of experiments through clear instructions, and serving as a collaborative resource for the RL research community, thereby facilitating the exploration and assessment of new RL methods. We delve into the Open RL benchmark, showcasing its diverse libraries and environments, and the metrics it tracks. We also highlight how it ensures accurate reproducibility and aids in creating data visualizations through its command line interface, CLI. The Open RL benchmark stores its data on weights and biases, organized into projects that may correspond to specific libraries or more specialized runs. For instance, one project might focus on runs using the NVPool environment implementation, while another might be dedicated to a reference implementation like TD3 or phasic policy gradient. The benchmark also features interactive reports to help visualize and analyze results more effectively. At the time of writing, the Open RL benchmark boasts nearly 25,000 runs, amounting to over 72,000 hours, more than 8 years, of tracked data. The runs span a variety of reference RL libraries and a wide range of environments, from classic ones like Atari and MuJoCo to more specific ones like Bullet and MO Gymnasium. Metrics tracked in the benchmark are categorized into 4 groups: training-related metrics, like average returns and episode length; method-specific metrics, such as value loss and policy loss for PPO; evolving configuration parameters, like learning rate or exploration rate in DQN; and system metrics, including GPU memory usage and CPU usage. These metrics are linked with a global step and an absolute time, allowing for the tracking of the learning process's duration and progress. Section Summary. The section discusses the challenges in comparing new reinforcement learning (RL) methods with reference data due to the unavailability of data, insufficient source code documentation, and limited computing resources. To address these issues, the Open RL Benchmark Initiative offers a large, diverse collection of tracked RL experiments, emphasizes reproducibility and transparency, and provides comprehensive metrics, ultimately serving as a valuable resource for RL research. It contains nearly 25,000 runs, covering various RL libraries, classic environments, and tracked metrics, and aims to enhance the visualization of experimental results through interactive reports. Section: Everything you need for perfect repeatability. We're here to talk about how to make sure that when you do an experiment in computational research, you can get the same results every time you try it. This can be pretty tough because often, the code changes, or maybe we don't have all the details on how the experiment was set up, or there are differences in the versions of the software used. We've come up with a way to help with this by making sure that when you try to do an experiment, you have everything you need to get it exactly right. This includes all the settings used in the experiment, the exact versions of any software needed, and even the specific command to run the experiment, right down to the random numbers used. We've also made a special tool in CleanRL that makes it easier to do an experiment again. It helps you set up your computer with everything you need, downloads the right files, and gives you the exact command to run. This is great for research because it lets us look more closely at things that don't happen often or are left out of the results for some reason. For those who are into reinforcement learning, RL, we've got something called OpenRL Benchmark. It lets you get raw data from RL experiments and makes it easy to turn that data into graphs that look good in research papers. You can do all of this with just one command. This tool is really handy for making graphs related to RL research, and we used it for all the graphs in this paper. You can also use your own scripts to get data from the OpenRL benchmark, which we talk more about in the appendix. Now, let's talk about how OpenRL benchmark can be really useful with a couple of examples. First, we looked at how different ways of estimating value in an algorithm called PPO can affect its performance. This is something people haven't really studied before. Then, we showed how OpenRL benchmark can help show the benefits of a new way to do something called Impala, which can make things faster and more consistent. In the first example, we compared two methods for estimating value in PPO. One is called temporal difference, TD, with a lambda parameter, and the other is the Monte Carlo, MC, estimate. PPO uses something called generalized advantage estimation, GAI, to update its predictions. The advantage estimate and the target return for critic optimization are calculated using formulas that balance how much we trust the current estimate versus new information. We looked at how changing the way we estimate value affects PPO's performance by running experiments in different environments like video games and simulations. We found that changing the value estimation method does affect how well PPO works. For example, in video games, the new method wasn't as good as the original, but in simulations, it was about the same. This shows that the way PPO learns can be quite different depending on how we estimate value, and it's important to understand these differences when doing research in this area. Section Summary. The section discusses the challenges of reproducing experimental results in computational research and introduces an approach to enhance reproducibility by providing complete configurations, frozen dependencies, and a utility for experiment replication. Additionally, it highlights the OpenRL benchmark's utility in comparing different RL algorithms through case studies, showcasing its role in advancing RL research by providing insights and facilitating consistent and reproducible comparisons. Section: Demonstrating the utility of OpenRL benchmark through the CleanBA case study. We're going to talk about how the OpenRL benchmark was a game changer for evaluating and showcasing CleanBA, a new tool for distributed reinforcement learning, RL, that's open source and supercharges the performance of popular algorithms like PPO and Impala. First off, the folks behind CleanBA made three big claims. 1. CleanBA's way of doing things is more sample efficient compared to other methods. 2. It's optimized to run faster on the same hardware. And 3. It makes the results you get more consistent, reducing the ups and downs often seen in experiments. However, proving these points wasn't straightforward. A big hurdle in RL research is that many foundational studies don't share their raw data. Even though there are reference implementations out there, they're not kept up to date. While some projects like MooLib and TorchBeast have managed to replicate Impala's findings, they only shared smoothed-out graphs of their results from specific Atari games, which don't match the classic Atari 57 set, and didn't provide the raw data behind those graphs. Acknowledging this gap, the CleanBA team decided to rerun these Impala experiments themselves, carefully recording everything and adding it to the OpenRL benchmark. This wasn't just about the scores. They also documented the system setups and timing, which was crucial to back up their claim that CleanBA is more efficient. They then compared CleanBA's performance directly against these benchmarks on the OpenRL benchmark platform, even sharing the exact commands to recreate their graphs. The results? CleanBA not only matched the baseline performances but did so more quickly and with less variation across different hardware setups, proving all three of their initial claims. Switching gears, we also dive into the current state of data reporting, sharing, and replicability in RL research. Despite some progress, there's a lot of inconsistency in how results are presented, which can make it tough to interpret, compare, and replicate findings. We specifically look at learning curves, a common tool to show how an agent improves over time. We noticed that there's no standard way to present these curves. For instance, what's measured on the y-axis, the vertical line, can vary. Some studies sum up rewards during the agent's run, while others pause training to average out the rewards, which gives a clearer picture of performance. As for the x-axis, the horizontal line, older studies might track policy updates, but most now count interactions with the environment, like the number of frames in Atari games, adjusted for frame skipping. The way variability in data is shown also differs widely. Some use shaded areas to represent standard deviation, while others might show a range or use statistical methods to give a confidence interval. But not all studies are clear about these choices, which can make it hard to understand or trust the variability they report. Lastly, we touch on smoothing, a technique to make graphs easier to read by reducing noise. While it's helpful, it can also hide the true variability in the data. Unfortunately, many papers don't explain how they smooth their curves, if they mention it at all, leaving us in the dark about what exactly we're looking at. In summary, the OpenRL benchmark proved invaluable for validating CleanBA's performance and efficiency. Meanwhile, the broader issues of data reporting and reproducibility in RL research highlight the need for more transparency and standardization in how we share and interpret experimental results. Section Summary. The section demonstrates the effectiveness of OpenRL benchmark through the evaluation of CleanBA, a distributed RL platform. CleanBA's authors compared their implementation with baselines, showing better sample efficiency, faster convergence, and reduced variability. The section also highlights the challenges in RL research, such as inconsistent presentation of results, insufficient data availability, and issues with method reproducibility, particularly in plotting learning curves and defining data variability. Section: Normalization and Aggregation. We've noticed that when it comes to evaluating the performance of different methods across a variety of tasks and areas, it's really important to have a way to compare results fairly. This is especially true outside of specific areas like Atari games, where there isn't a common way to normalize or combine results. Without a standard way to do this, people often don't combine scores at all, or if they do, they use a simple method that doesn't really tell us much about how good one method is compared to another. In the past, Atari studies didn't normalize or combine results either, but more recently, there's been a move towards comparing performance to human players. This approach isn't perfect, though, and might not fully show how well an agent is doing. When it comes to combining results, using the average is common but can be thrown off by very high or very low scores. Some studies use the median instead, which is less affected by outliers, and nowadays, it's not unusual to see both average and median scores reported. A newer method uses something called the interquartile mean for a more balanced view of performance across different games. Talking about sharing data, most studies only share the results shown in their papers, which means anyone wanting to compare methods has to rely on libraries that try to replicate these results. Some libraries give a good overview or visual summary but don't share the raw data. A few platforms are better at sharing data, like Dopamine and Sample Factory, which provide detailed data and even trained agents, making it easier for others to reproduce and build on their work. Reproducibility is a big topic in research. Some older and even newer studies don't share their code but give enough details that you could try to recreate their work. However, not sharing certain settings or the specifics of how something was implemented can make a big difference in performance and makes it hard to tell if improvements are due to new methods or just different coding choices. The research community is trying to do better by asking for more detailed reporting and sharing of code, but maintaining these codebases after publication can be a challenge. Libraries that bring together many standard methods are helpful, but ensuring these methods can be reliably repeated over time is still a work in progress.